Hello and welcome. We all think of computers as just being ridiculously fast, but that's not their real secret. Their true superpower? They are masters of organization. So today, we're going to pull back the curtain and look at the clever tricks computers use to manage information. Everything from solving a maze to running a massive database. All right, let's just dive right in.
So, let's start with the big one. Seriously, picture a billion customer records. A billion! If a computer had to check them one by one, you'd be waiting for days, maybe weeks. But it doesn't. You click, and bam, there's your info. How in the world did they do that?
Well, you guessed it. It's not magic. The secret isn't just raw speed. It's all about the structure. Computers use these brilliant methods called data structures to arrange information in a way that makes finding it incredibly fast and efficient. And we're about to explore some of the coolest ones.
Okay, first up, how does a computer keep track of things when it's juggling a bunch of tasks at once? When one big job is made up of lots of little jobs, how does it remember where it left off so it can come back and finish everything?
Well, let's imagine you've got this situation. A giant pile of dishes after a fancy dinner. This is actually a fantastic way to visualize how a computer thinks through a complex problem. You can't just attack it randomly. There's a natural order to things. So let's walk through it. You grab the big plate at the bottom, right? But wait, there's a saucer on it. And on that saucer, there's a spoon. So what do you do first? You wash the spoon. Then you can wash the saucer. And only then can you finally wash the plate you started with. Notice that. The very last thing you dealt with, the spoon, was the very first thing you finished.
This exact principle is what computer scientists call last in, first out, or a LIFO. And it's the rule for a super important data structure called a stack. Just like our dishes, the last task a computer puts on its to-do pile is the absolute first one it takes off and finishes. This is totally fundamental to how computers handle nested problems. A great way to think about this is like leaving a breadcrumb trail. Imagine a computer trying to solve a maze. Every time it comes to a fork in the road and makes a choice, it drops a breadcrumb on the stack. If it hits a dead end, no problem. It just backs up, picks up its last breadcrumb, and it knows exactly where it was and which path to try next. It literally can't get lost. All right, so using that stack idea, let's talk about something a little weird, the way computers do math. See, they don't really understand 5 plus 3 the way we write it. For a machine, having the plus sign in the middle is actually kind of awkward. Computers kind of prefer to speak like Yoda. We say, hit the nail with the hammer, with the action hit in the middle. A computer would much rather hear hit, nail, hammer, or even more commonly, nail, hammer, hit. This is called prefix and postfix notation, and it puts the action, or the operator, either at the very beginning or the very end. So why this bizarre grammar? It's all about efficiency, my friends. Using postfix notation, a computer can just scan an equation from left to right one time, no backtracking. It doesn't need to worry about parentheses or the order of operations. It just puts the numbers on a stack, and as soon as it sees an operator like plus or times, it just grabs the last two numbers and does the math. It's simple, it's fast, it's elegant. So now that we see how computers can remember their path, let's really dig into how they solve those huge puzzles that seem to require a ton of trial and error. This is where that whole breadcrumb trail idea really shines. Take the classic 8 queens problem. The goal is to put 8, count them, 8, chess queens on a board so that none of them can attack each other. That means no 2 queens on the same row, same column, or same diagonal. Where would you even start trying to solve that? Well, a computer uses a beautiful strategy called backtracking. It's a really systematic way of exploring all the possibilities without going crazy. It'll just try placing a queen in a spot, then it moves to the next column and tries to place another one. If it ever gets stuck where there are no safe spots left, it doesn't panic. It just backs up to the previous queen, moves her to a different spot, and tries again from there. So you see, it's exactly like solving a maze. You go down one path as far as you can. If it leads to a solution, great. If it leads to a dead end, you just calmly retrace your steps to the last place you made a choice and you take a different turn. It's trial and error, but it's organized trial and error. It guarantees you'll find a solution if one exists. Okay, let's shift gears from puzzles to the real world. Let's talk about networks. Things like power grids, the internet, roadmaps. Computers are constantly optimizing these things for us. But what optimal means can be two very different things. Just look at these two goals. On one hand, you might have the problem of connecting every single house in a new neighborhood to the power grid using the least amount of expensive cable possible. On the other hand, you might just want to find the single fastest way to get from your house to your friend's house across town. These are fundamentally different problems that need different solutions.
And that's really the core distinction here. An algorithm designed to find a minimum spanning tree, or an MST, is optimizing for the total cost of the entire network. But an algorithm to find the shortest path is optimizing the cost for just one specific trip between 2 points.
Here is the absolute best way to remember this. Think power grid versus road trip. A minimum spanning tree is the power grid problem. How do we connect everyone for the lowest total cost? The shortest path is the road trip problem. What's my personal fastest route on the GPS to get to work? Same map, two totally different goals, and two totally different answers. All right, for our last little mind bender, I've got a classic gotcha question from Computer Science 101. It really gets at a fascinating kind of two-faced way that data can be stored inside a computer.
So here's the question, and it seems super simple. You have something called a linked list. All it is a sequence where item A points to item B, and item B points to item C, and so on. So, is it a straight line?
Logically speaking, yeah, of course it is. When you use it as a programmer, you follow it in a straight line. You start at A, you go to B, then you go to C. It's a perfectly clear linear sequence. But that's only one side of the story.
Because the real question, the gotcha, is this. What does that list actually look like physically inside your computer's memory chips? If you could crack open the RAM and look, would you see A, B, and C all sitting neatly next to each other in a row?
And the answer is almost certainly not. Physically, a linked list is way more like a treasure hunt. Node A could be sitting way over here in memory, and all it holds is the data for A and a little pointer, a clue, that tells the computer the memory address for node B, which could be way over there. And B holds the clue to find C. The pieces are actually scattered all over the place.
And this brings us to this really cool final idea. A linked list is logically linear but physically nonlinear. It's both at the same time. It just depends on how you look at it. It gives the programmer a nice, simple straight line to work with, while underneath it's managing this chaotic, scattered reality in memory. And that's really what all these tricks are about, creating simple, powerful logic out of physical complexity. Thanks so much for watching.